The solution here is IT is equal to A, which is the amplitude we just figured out is Vm divided by square root of R squared plus omega squared L squared, and times a cosine omega t plus phi, and the phi is inverse of tangent negative omega L divided by R. Now you see that's quite lengthy. So what we want is that we wish to somehow simplify that process. So what we want is we want to introduce a complex function. First, we want to review the Euler's equation. Euler's equation that e to the j x is equal to cosine x plus j sine x. Now, j is the complex number. It's defined by square root of negative 1. The reason we don't use I in the complex number is because the I, often we use current in the circuit class here, so we all use j to represent that negative 1. In mathematics, you probably have not seen j. We always use I is equal to negative 1, square root of negative 1. But because in circuits class here, we're using I to be our current. So we don't really want to confuse ourselves with a complex number. Therefore, in this class, we always use j to represent that complex number. All right, now, when we look at this one here, we actually know that the exponential function is much easier to deal with than the sinusoidal function. But we recognize here this is the real part of it, which is our real function. And what do we assume? Our voltage given is equal to Vm e to the j omega t. We assume that, which you can see is not true. It only actually carries the real part of it, but that's okay. After we solve the solutions, we only take the real part. You can see if we expand that, we have Vm times cosine omega t plus j times Vm times sine omega t. Now, after we solve our equations, we only take the real part. This is the actual function given. So what happens if we do that? Then we can say, well, current can be assumed accordingly that IT is equal to Im, which is our A, and e to the j omega t plus phi. And that gives us Im times cosine omega t plus v plus j times sine omega t plus phi. You can see if we figure that out, we find the solution, we take the real part. And that actually is our solution. So now what we can do is that we're going to use just that exponential and try to solve the differential equation 1 again. So di dt in this case is simply just equal to j times omega Im e to the j omega t plus phi. That's the derivative with respect to t. Remember, the derivative of e to the jt is just equal to e to the jt. So the derivative of exponential here is just equal to e to the jt, right? And then multiply by the j. All right. So now we're going to put it back into the equation. We have the L times j, L di dt, that will be L times j times omega times Im, and e to the j omega t plus phi, and then plus r times the I, which I is equal to Im e to the j omega t plus phi, and that is equal to Vm e to the j omega t. So now from that equation, you can see quickly, you notice that e to the j omega t, that just equal to e to the j omega times e to the j phi. Now all these terms is the same thing, and you can see they all have the common terms of e to the j omega t. E to the j omega t here times e to the j phi, and here we have e to the j omega t. So every term has the common term of e to the j omega t, e to the j omega t, e to the j omega t, and therefore the coefficient that we have left is just L j omega Im times e to the j phi plus Rim e to the j phi is equal to Vm. So I am e to the j phi multiplied by, we're going to take that factor out, we're going to factor this out here, and that just equal to j L omega plus R, and is equal to Vm. And so we can write it again. We say I am e to the j phi is equal to Vm divided by R plus j L omega. Now, of course, we can get rid of this one, the j in the denominator, by multiply a complex conjugate. So we're going to multiply R minus j L omega, and numerator, we're going to apply the same term. And so denominator will end up with R squared times plus j times L times omega, that squared. But remember, j squared is equal to -1 times -1. That end up with -1. So we have the denominator is R squared plus L squared omega squared, and then Vm times that R minus j L omega. All right, now we're going to assume we're going to actually take another form. Remember, this is the real part and the imaginary part. So we're going to let this one here, the R minus j L omega, to be expressed in terms of some constant multiplied by e to the j theta, which can be written as k times cosine theta plus j k times sine theta. So now you can see from there that we know k is equal to square root of r squared plus omega squared L squared. That's the magnitude. Remember, we did that in the previous solution. And tangent theta is equal to negative omega L minus R. Now we can actually make comparison now. So let's copy this part so we can make comparison. On this side here we have that complex, the exponential form. On this side here we obtain also the complex form, the exponential form, because we convert that into k times e to the j theta. So from there, we can gather that Im would be the magnitude, which compare on this side here. That would be this term. That would be this term here. The Vm, this term here, the Vm, the amplitude here, the Vm divided by r squared plus L squared omega squared, and then multiplied by k. Remember, this one is expressed in k times e to the j theta, and k is equal to square root of r squared plus omega squared L squared. So we simplify that, and we end up with exactly the same thing as we obtained earlier, and that will be square root of r squared plus L squared omega squared. Now the phi is the theta. The phi is the theta. So phi is inverse of tangent of negative omega L divided by r. Now if you compare the way we solved it, the exponential is much quicker and shorter. So that leads to a next expression. That would be phasor.